Hello, Algebra 2 students. I gave you a video to watch about matrices last week, and I hope it wasn't too confusing. But that's what I want to talk about today. That follows on from what we talked about with systems of equations previously. And as we go on, you'll see what I mean. So I want to talk a little bit about matrix algebra today. And when I say matrix, I don't mean like a Keanu Reeves movie where you can dodge bullets and stuff. Sorry, I can't teach you how to do that. But this is almost as much fun as that. Well, maybe not, but we'll see. Okay, we all have seen things like this where you would have some kind of a chart. Say Jack and Jill and Bob and Sue. You have a table. And maybe this table is their grades. So maybe the first column is quiz 1. The second column is quiz 2. The third column maybe is quiz 3. And they have their grades, whatever those might be. We've all seen tables like this. It could be a table of grades. It could be a table of numbers, phone numbers, addresses, whatever. That's all a matrix is. A matrix is a table boiled down to its essential facts, which are the numbers. So a matrix, you might just have the grades alone. 90, 85, 91, 95, 83, 89, 85, 88, 86, 91, 92, 93. And when we have a matrix, we put square brackets around it. And there you have it. So that's just a very simple example of what a matrix would look like. It's just a bunch of numbers in a chart form, but without the actual chart. Okay. So any kind of chart, you have rows and columns, like you just now saw. So the simplest matrix would just be one number, obviously. And that's not something you would actually see very frequently. You could, but probably not. So you might have a matrix which can have negative numbers with 2 columns or 3 columns. You could actually have fractions too. Fractions are your friends, you know. And you could have different numbers of rows. The more interesting matrices usually have more than one of each. Let's say you've got 3, -2, -5, 6, 8, 12. Okay. So this matrix has 1, 2 rows. And let's call this matrix, let's call it matrix M for matrix. We'll be very creative there. So we use all this stuff, by the way, is in your book, page 146. Page 146 in your textbook. Just so you know where I'm coming from. So lowercase m is the number of rows. So this matrix has two rows. Here's one row, there's another row, very obviously. And then n is the number of columns. 1, 2, 3 columns. So this guy has 2 rows and 3 columns. We say it is a 2 by 3, writing the words out, 2 by 3 matrix. So the number of rows comes first, 1, 2, by the number of columns, 1, 2, 3. And the way we write that is the same way we would write it if you've ever seen a piece of lumber, a 2 by 4, a 3 by 6, something like that. Excuse me. They use the multiplication symbol, the x, to mean by. So 2 by 3. And you could even say M is 2 by 3. And that tells me that matrix M has 2 rows and 3 columns. As simple as that. And these are called the dimensions. The dimensions of that matrix. Okay. So one thing would be to identify the dimensions of a given matrix. And by the way, when you're doing things with matrices, you have to leave yourself a reasonable amount of room. You know, in an ordered pair, like a point on a graph, we use parentheses and we use a comma to separate them. In matrix algebra, we have nothing to separate the numbers. So you have to have a little bit of a space. You don't want that to look like 30. You would not want to do that. Where it looks like 30 and 59, that's no good. So can't do that. You need to space them appropriately. So this has 2 rows and 2 columns. It's a 2 by 2 matrix. Let's call this M for matrix. Maybe this is N. This is a 2 by 3 matrix, 2 rows and 3 columns, like the one we drew earlier. Let's say you have matrix P that looks like this. Now that is a 3 by 2 column. It has 3 rows and 2 columns. So obviously 2 by 3 is not the same dimension as 3 by 2. It makes a difference which way it goes, so that's very important. So this is just examples of identifying the matrix, its dimensions. Sometimes and what I'm doing now is still on page 146. If we want to identify just some generic element, it didn't look like a nice letter. If we want to identify some generic element in a matrix, we can use the letter A and the little subscript number. The first digit tells me the row, and the second digit tells me the column. So 1, 1 means first row, first column. 1, 2, first row, second column. You could imagine a graph. If you imagine the matrix being kind of a table like this, where this is row 1, row 2, row 3, column 1, column 2, column 3. So this is 1, 1, 1, 2, 1, 3. 2, 1, 2, 2, 2, 3. See what I mean? 3, 1, 3, 2, 3, 3. So if I just said in some matrix, if I said I had a 5 by 7 matrix, and I said element 4, 5, what that would mean is I would look at this matrix, I would look at the 4th row, 5th column, down 4 rows, 1, 2, 3, 4, then over 1, 2, 3, 4, 5 columns. So whatever was in this position would be 4, 5. I know this may sound a little bit confusing now at this point, and I understand that. The thing you've got to remember is this is just notation. We're not even actually doing math at this point. What we're doing is we're just giving the terminology for how we write this stuff. Okay. So what I want to do now is look at how we make operations, mathematical operations with matrices. So first off, suppose we had something like this. Let's do a 2 by 3 matrix because we want to keep it simple. And let's set it equal to another matrix. Say, and you see an example like this. There are some examples like this in your textbook starting on page 155. Page 155, FF. FF does not mean Fantastic Four. FF is a symbol you see, and you'll see this in books when you get to college. FF means and following. So P155FF means page 155 and the following pages. So, let's see. And I'm following, let me see. I believe the format they are using here. Okay, I'm departing from what the book is doing. So let me just do this. Let me be consistent. In the book, they're using different variables, which really is probably what I need to do. So I'm going to have this y plus 5z minus 3, w over 2, m minus 10, a over 2, and b minus 8. Okay, so basically, each number corresponds to the expression in the corresponding place in the other matrix. So if we call this matrix A and this is matrix B, well, this position is A11, and just to distinguish, I could say B11. Remember, row and column, row and column. So I can just set them equal. 3 equals y plus 5. So solving that as usual, y equals -2. And from this point, it's actually quite boring. You just go through and match up each positions, A11, B11, A12, B12. So this is A12, this is B12. Match them all up and set them equal and get what they're at. Get what the variable is. 4 is equivalent to z minus 3. So you add 3 to both sides and you get z equals 4. And then you get negative 5 equals W over 2. Multiply both sides by 2 over 1. So W equals negative 10. And then M minus 10 equals 7. I'm writing it in different order just because I can. M equals 17. 10 equals 8/2. As I'm slowly running out of room. Multiply both sides by 2 over 1. So A equals 20. Guess I should be circling all these answers. Just kind of to be a good citizen about it. Got 1, 2, 3, 4, 5 answers. There's one more answer, 6. So actually, I can't have 2 variables. I forgot that I had the variable here. So let's put this back to what it was. So x plus 2 equals negative 8. Subtract from each side, x equals negative 10. So really, this is pre-algebra, the actual solving these out, like 3 equals y plus 5. That's pre-algebra. It's very simple stuff. The only thing is you have to figure out which positions, like this position to that position. This position to that position. This position to that position. This position matches to that position, so forth. All you have to do is match the corresponding positions in each matrix, and then you solve for the variables. Easy as that. Now, I want to talk about addition, subtraction, and scalar multiplication. I forgot to change my pen color, but hey, we can do blue. We can be different for a change. So suppose I have C, and it's let's say it's a 2 by 3 matrix. 3, negative 4, 5, negative 6, 8, negative 10. And let me say I say D equals 2, 3, 4, negative 7, 8, 0. Okay. Addition, C plus D. Addition's the easiest thing in the world. You just add corresponding parts. So I could say 3 plus 2 for the A11 place. Negative 4 plus 3. So this to this, this to this, this to this. 5 plus 4. Negative 6 to negative 7. That's plus a negative 7. 8 to 8. 10 to 0, negative 10 to 0. So C plus D is that. And then I just add. 3 plus 2 is 5. Negative 4 plus 3 is negative 1. Subtract, take the sign of the larger absolute value. 5 plus 4 is 9. Negative 6 plus negative 7. You add them and keep the same sign. 13, negative 13. 8 plus 8 is 16. And the hard one, negative 8 plus negative 10 plus 0 is just negative 10. That is all. Nothing at all hard about that. That's how you add. You just add position-wise. So, let's get rid of this and do subtraction. If you have guessed already that subtraction is just going to be doing the same thing, subtracting position-wise, just like we just added position-wise, then you are exactly correct. That's exactly what happens, which is equivalent to changing the signs in the second position. So let's say C minus D equals 3 minus 2. Now this is kind of conventional. They're both positive numbers and 3 is bigger. Negative 4 minus 3. Negative 4 minus 3. 5 minus 4. Boy, that's a horrible looking bracket. Negative 6 minus negative 7. 8 minus 8. And negative 10 minus 0. Well, okay, so what do we get from that? 3 minus 2 is 1. That's the easiest thing in the whole matrix. When you're subtracting, just as a reminder, it's like you're at 1, 2, 3, 4. You're at negative 4. Subtraction means you go in the negative direction, 1, 2, 3. So you end up at negative 7. So it's equivalent to saying plus negative 3. Just a little reminder of how your negatives and positives work. 5 minus 4 is 1. Minus a minus is a plus, so that turns into 6 plus 7, which is 13. 8 minus 8. I said this was the easiest. That's probably the easiest. 8 minus 8 is 0. Negative 10 minus 0 is not affected. So there is your answer matrix there. So it's a little bit more work than adding because you do have to change your signs and you have to remember your rules of positive and negative numbers, but still no biggie. Last, scalar multiplication. So, whoops. I still want to keep working with these same guys because that way I don't have to make up a new matrix. Scalar now, for those of you guys who are in my physical science class, I think I've mentioned this term. If I haven't, shame on me, you'll hear it now. We've got two concepts, scalar and vector. Scalar has no direction. Vector has direction. And the way we're using those terms here is not quite exactly the same way we use them in physics, but there's a similarity. So we're not quite ready. We're not quite ready to say matrix C times matrix D. That gets kind of complicated, and it's not what you think it is. You're probably thinking, well, when I added, I said 3 plus 2. When I subtracted, I said 3 minus 2. So when I multiply, it's going to be 3 plus 2. It's a good idea, but it's wrong. And I'm not going to talk about that today. So that's not actually going to happen. But what I am going to talk about is if you had something like this. 3 times matrix C. And let me see if I'm using the correct terminology using the dot the way your book shows it. So, they're not even showing the dot, so it's okay. So what I could do is just get rid of that 3C. Well, took out my 3 as well. That's all right. So if I want to say 3 times matrix C, I would write 3, and then I would write my entire matrix like that. And if you want to see some examples of this in your textbook, pages 152 is where that would be. Okay. Yeah, there's some examples on page 152. And that's easy. What you do is your coefficient here times everything. So you'd have 3 times 3, 3 times -4, 3 times 5, 3 times -6, 3 times 8, and 3 times -10, all of which is very easy. You're going to get 9, -12, 15, -18, 24, and -30. Very easy. So that's very, very easy. Let me do another example. Let's do something with D. Let's see if we can do something with D. And keeping in mind my typical dictum, fractions are your friends, I'm going to say 1/2 D, or 1/2 times all this stuff. So that is 1/2 times 2, 1/2 times 3/1. I'm going to rewrite it. I guess I should be consistent and rewrite these all as fractions, just to be nice about it. 1/2 times -7/1, 1/2 times 8/1, and 1/2 times 0. Well, your 2's cross cancel, and you just get 1. This gives me 3/2, which is 1.5 or 1.5, but I'm going to leave them as improper fractions. That cross cancels and gives me 2. Going to give me -7/2. That cross cancels and gives me 4. And of course, anything times 0 is just 0. So it looks intimidating, but it doesn't have to be. It is not a problem at all. Let me do one last example. And I'm going to do this out of your book. This is on page 153. And when I write it, it's going to look horrible, but trust me, it's not. They say solve for x. So they've got a matrix. The first matrix is 2, 1, 3, 3, 5, 1. 2, 1, 3, 3, 5, 1. Minus 2x equals 3, 5, 2. 3, 5, 2. 1, 4, 1. And you look at that and say, oh my goodness, good heavens, that looks like the most horrible, most awful thing ever. And actually, there's one slight thing I should have done. I need to make that be a capital X, because the answer is going to be an entire matrix. Now, let me kind of do something else over here. Suppose I had 3 minus 2x equals 9. What do? I want to get the x by itself. So that brings us to SAM, which you've seen me do a zillion times. Simplify, add, which includes subtraction, and multiply, which includes division. No different here. I take care of my subtraction or addition first. So I get -2x equals 6. 9 minus 3 is 6. Then I divide both sides out by 2. Or an alternate way you could look at that is that I multiply both sides by negative 1/2. Same thing, 2's cancel out, x equals negative 3. 2's cross cancel, negative times a negative is positive. 2 cross cancels with the 6, x 3 times negative 1 is negative 3. Same answer either way. Well, this mess over on the left is the same as the right, only with matrices. So just like here, I had to get rid of the 3 first. I have to get rid of that whole matrix. So I'm going to say negative 2x equals okay. Negative 2x equals this here, 3, 5, 2, 1, 4, 1, minus that whole deal. 2, 1, 3, 3, 5, 1. I'm not writing the subtraction over here because it would take up too much space. I did the same thing, though. So I get negative 2x, and I just do what I did before. I subtract position to position. 3 minus 2 is 1. And I hope you're following this. I don't have room to write out all the steps, but I think it's clear. 5 minus 1 is 4. 2 minus 3 is negative 1. Let me double check something here. Make sure. Yeah. 1 minus 3 is negative 2. 1 minus 5 is negative 4. And 1 minus 1 is just 0. Well, I have to get rid of the negative 2. I have to get x by itself. So I multiply it by negative 1/2, which means I have to multiply this whole thing by negative 1/2. So that leaves me x by itself. Negative 1/2 times 1 is negative 1/2. Negative 1/2 times 4, half of 4 is 2, it turns negative. Negative 1/2 times negative 1, negative times a negative is a positive. Negative 1/2 times negative 2, they cancel out, give 1, negative times a negative is a positive. Negative 1/2 times negative 4, half of 4 is 2, and the negative times a negative is a positive, so they cancel out and give a negative. And then finally, negative 1/2 times 0 is 0, of course. So this here is your grand finale. That is your answer. Okay. I hope this has not overwhelmed you too much. I hope it makes sense. I will give you a small number of problems, a very small number of problems for you to work over the next day or two dealing with this to give you time to assimilate it. This may all seem like very strange, abstract stuff at this point, and I would not blame you for feeling that way. I kind of felt that way about it the first time I encountered this myself, and I didn't have matrices like this till I was in college, if I remember correctly. But you will see when we get to a certain point that there is a reason we have for doing this, and it can make certain things very easy. So I'll let you go at that. I will talk to you the next time, and clear my board out. And that's all. See you later. Bye.